We will now take a look at how the Twin Independent Variable Cam Timing, or Ti VCT, works on the Ford Duratec 1.6 litre double overhead cam engine. The Ti VCT system is used for changing the timing of the intake and exhaust valves relative to the engine ignition at top dead centre during a complete engine cycle. In the case of the Ford double overhead cam engine, the Ti VCT uses the intake camshaft phasing to advance the intake valve opening and the exhaust camshaft phasing to retard the exhaust valve closing. The basic Ti VCT system is mounted onto the camshafts at the front end of the engine. There are individual VCT units for both the intake and exhaust camshafts. The generic hydraulically driven Ti VCT units are bolted to the drive side of the camshaft and are located inside the camshaft timing belt gear. The VCT unit consists of a housing and a rotor with 4 fixed vanes. The housing is bolted to the belt sprocket, thus rotating with the engine. The rotor vane is bolted to the camshaft. The rotor vane fits into the housing. There, it can rotate relative to the vane housing, typically between 45 and 50 degrees crank angle. This relative rotation allows the intake and exhaust cams to independently move in the advance or retard direction during engine operation. The rotor wings divide the housing into separate chambers called advance and retard. When the advanced chambers are pressurized with oil, the valve timing is advanced. Conversely, when the retard chambers are pressurized with oil, the valve timing is retarded. The chambers are fed with pressurized oil supplied by the engine's oil pump. By controlling and varying the oil flow into and out of the advance and retard chambers, the rotor vane position and the valve timing will change accordingly. At engine cold start, the VCT system is in a passive mode where both camshafts are locked into basic engine timing positions. This is done with a spring-loaded locking pin in each of the VCT units, which lock the rotor vane to the vane housing. When the engine is turned off and during extreme engine operating conditions, the VCT system locks into the passive mode. This engine running mode results in minimum valve overlap, meaning that the intake valves open late and the exhaust valves open early. The Ti VCT system, being in either active or passive mode, is controlled by the powertrain control module. Depending on the engine's temperature, speed and load situation, the powertrain control module activates the VCT system. Activation is done by exposing the locking pin to pressurized oil, which will push it down and release the rotor vane from the housing. When switching back to passive mode, the oil pressure decreases and the locking pin snaps back into locking position. To control the oil flow into and out of the VCT chambers, each VCT unit has its own oil pressure control valve, or OCV, which is mounted onto a special camshaft bearing bridge. The oil control valves direct the flow of oil through 4 different channels: an incoming oil channel, an oil channel connected to the advanced chambers of the VCT unit, another connected to the retard chambers, and a channel that drains oil back into the cylinder head. A control plunger is located inside the oil control valve. The plunger works as a hydraulic 4 to 3-way proportional valve. The position of the plunger determines how the pressurized oil is directed through the VCT system. Let's take a closer look at how the elements of this system work together to change the timing of the intake valves. While the engine is running, pressurized oil is fed into the oil control valve by the engine's oil pump. When the plunger is in its mid position, known as the hold position, the oil flow is turned off to all the other oil channels. If the plunger is moved forward, the pressurized oil is released into the channel that is connected to the advance chambers in the VCT unit. From the oil control valve, the oil travels through holes in the first camshaft bearing bridge to a channel surrounding the camshaft. The oil then passes through holes within the camshaft and then through channels in the rotor vane and finally reaches the advance chambers. If the plunger in the oil control valve is moved backwards, the pressurized oil is released into the channel that is connected to the retard chambers. In this scenario, the oil reaches the retard chambers in a similar manner, but by a different route. As the plunger allows pressurized oil into the retard chambers, it simultaneously opens the oil channel connected to the advance chambers, draining oil back to the cylinder head. The oil pressure difference between the chambers makes the rotor vane and camshaft rotate into a late phasing direction, making the valves open later. Conversely, when the plunger allows pressurized oil into the advance chambers, the oil in the retard chambers will be enabled to drain back into the cylinder head. This causes the rotor vane and camshaft to rotate into an early phasing direction so that the valves will open earlier. When the plunger moves back into the hold position, it will stop the oil from flowing in and out of the chambers in the VCT unit, and the oil pressure in all chambers will equalize. This action will stop the camshaft from rotating relative to the housing and therefore hold the camshaft timing in the current position. The oil control valve actuation and the camshaft position are controlled by the powertrain control module, or PCM. It sends out signals to the oil control valve's magnetic solenoid driver to tell it to either open or close the different oil channels. The powertrain control module constantly receives information from two camshaft position sensors, which are mounted on the valve cover, and from a crankshaft sensor to determine the camshaft timing relative to engine top dead center. Data from all three sensors are used to control the camshaft timing. The Ti VCT control system hardware and software applies closed-loop control to ensure optimum cam timing under all engine operating conditions. The control system is able to change the cam timing at a speed of less than 0.2 of a second from the most advanced to the most retarded position.